Okay, YouTube, in this video we're just going to work through some examples of solving exponential equations, starting with some pretty basic forms and then kind of building up, and then also looking at an example of Newton's law of cooling. So let's go ahead and take a look at number one here. When it comes to solving exponential equations, certainly the very first thing we always want to check for is, do we have more than one base? And if so, if we had more than one base, could we write them on both sides and make the bases equal? That way we could imply that the exponents themselves would be equal. And so for number one here, I noticed that 2 to the power of x, okay, there's our b to the x expression there. Could we write the right side here as being 2 to the power of something? Because if so, then we would already know the answer for x there. It would be whatever the exponent is that we took 2 to the power of to get 5. Now, of course, if we knew what we could take 2 to the power of to get 5, we wouldn't be sitting here trying to solve this equation in the first place. But we do need to ask, can I write 5 as a power of 2? But because we cannot, what we're going to end up doing instead is using logarithms. So we're going to use logs to undo our exponential expression here. And to be very, very clear on this, the very first thing we have to do is isolate the base of our exponential expression. So because 2 to the x is already by itself on the left-hand side, it's in that b to the x form, what we'll do is we'll take the log base 2 of both sides of this equation. So we get log base 2 of 2 to the x is equal to log base 2 of 5. And what we end up saying is that this logarithmic thing with base 2 cancels out with the exponential thing of base 2. And we just get left with x equals the log base 2 of 5. So the fabulous part about this is that because of our change of base formula, we can just go ahead and rewrite this as the log of 5 over the log of 2. We'll just check this out on the calculator right here. So let's go ahead and take a look. Log 5 over log 2, log 5 divided by log 2. We get approximately 2.322-ish. So we're going to go ahead and write that down. And the thing here that's important to me is that we check our solution. So if we were to plug this back into the original initial equation here, would we get a true statement? And of course, if we were to take 2 to the power of, well, I guess we got 2.322-ish. We would round it up. We should be a little bit north of 5, which we are. But you can see that we get an approximate solution after 3 decimal places. And so let's go ahead and also make this other note here. We'd say that exponents out to 3 decimal places is a good plan because we get pretty accurate answers there. So looking at number 2 here, I notice 7 to the power of 9 times x is equal to 15, and 15 is not easily written as a power of 7. So again, what I want to do is isolate the base here, and because 7 to the power of something is already by itself on the left-hand side of this equation, what we'll do is very much the same thing we did in the last problem here is we'll take the log of both sides, except for in this case we want to be very clear, we're going to use a log base 7 on both sides just because what we have here is an exponential expression base 7. So with our log and exponential thing canceling out due to being inverses, we get left with 9x equals log base 7 of 15. Now here's the thing with this one is that we're just not done yet because we had a coefficient of x. So we'd say that truly our answer is log base 7 of 15, but split 9 ways. And so one thing that I'm going to do here is this. I'm going to go ahead and say that this is really log of 15 over log of 7 divided by the log of 9. But what that's going to do is it's just going to create a mess. So I'm going to make a suggestion that if you ever had the log of something like this over that 9 right there, either evaluate it separately, or what we'll do is we'll say it's just 1/9 times the log base 7 of 15, and we'll throw that 1/9 out front. So with our log of 15 over our log of 9 using our change of base formula here, what we end up with then is this. We get that log 15 divided by log 9, so log 15 divided by log 9. And we could actually do this, whoops, let me get it in there right. I forgot my parenthesis on my 15 here. That would have been bad. Divided by log of 9. What we end up with is this decimal right here, and I can take this times 1/9, or I can go ahead and I suppose divide it by 9. I just want you to see that you need to do your change of base first and then divide by the 9 and multiply by 9. So we get approximately 0.137. So we're going to write down that x is approximately 0.137, and I would encourage you to go back and check that in the original equation. Take it times 9, raise 7 to that power, I bet you get 15. Close-ish. Now for this last equation here, what you're seeing is that we have a base of e in our exponential expression, this thing where we're looking for the variable up in the exponent. So since the base is e, we're going to have to either rewrite both sides as having a base of e, or which is not going to happen, or we can take the log base e of both sides. But the thing here is our base is not by itself. So we see that we have a constant, this -7 here, and we see that we have a coefficient on our e here of 4 that we're going to have to get rid of first. So let's go ahead and isolate the base. We're going to do this. I'm going to rip this out to the side here. We say 4e to the negative 0.3x minus 7. Minus 7 is equal to 13. We'll go ahead and add 7 to both sides of this equation. So of course we get 20 on the right-hand side. We say 20 is equal to 4e to the negative 3/10 x, and then we're going to divide both sides by 4. Once we do this, then essentially what we've done is everything we need to up in this point is isolate the base. So now that the base is isolated, what we're going to do is we're going to take the log base e of both sides, everything on both sides. That means the 5 on this side, that means the e to the negative 3/10 x on this side. Now, because we're taking the log base e of e to the power of something and logs and exponential expressions, they're inverses of one another, what we get left with is this negative 0.3x equals the ln of 5. So just as we would to isolate x in any other equation, we would go ahead and divide by this coefficient that it has out here. And we end up with, I suppose we could say this is an exact value here, the ln of 5 over negative 0.3. And so what we end up with is a decimal. Let's go ahead and take a look at it as a decimal. We would get the ln of 5 divided by negative 0.3. And what we end up with is approximately negative 5.365. So x is approximately negative 5.365. Cool. Okay, so looking at this last example, it said that in example 2 in my last video, how long, it said would it take to cool a stew to 100 degrees Fahrenheit when the room temperature is 75. So in the last video, what we did was look at this Newton's law of cooling. And I'm going to go ahead and write this out here. It said that the temperature at any given time is equal to the initial temperature minus the room temperature times e to the power of negative RT plus the room temperature. So essentially what we were seeing was that our rate in the last video was 0.046. And we were given a room temperature. In this case, I suppose the room temperature has changed to 75 degrees. It shows that we want the actual temperature to be 100 degrees, and we would say, oops, this is TR, our room temperature here. And then our initial temperature here, in the initial example, let me show you here, the initial temperature was 212 degrees, or the boiling point of water in Fahrenheit. So with this right here, what we're doing is we're solving for T. We're saying how long would it take to do this? Let's go ahead and plug in all of our knowns. We say if we want our temperature to be 100 degrees here, then the initial temperature minus the room temperature of 75, not 70, okay, it would, let's see, negative rate times time. I'm going to plug in our rate, 0.046 times time. And this is all plus the initial room temperature, the room temperature of 75. So simplifying this part first here, let's get our calculators. Clear all this out. We'd say 212 minus that 75. So we have 212 minus 75. It's equal to 137. So we have 100 is 137 e to the negative 0.046 t plus 75. So now to solve this, we're going to clear everything out of the way of our base. We want to isolate the base. So we would say that 25 is equal to 137 e to the negative 0.046 t. Okay. So now we'll divide both sides by 137. And if you remember my advice from the last video, what we'll mention is that essentially you'll go ahead and leave this as a fraction. It's not worth getting a decimal because it'll just get messy. And we want, exact values regardless. So we say 137. There we say e to the negative 0.046 t. So now that we've isolated the base, what we're going to do is we're going to take the log of both sides. Since we can't easily write this as a power of e, we're going to take the log of both sides, but log base e. So to be clear, we're taking the ln, or the natural log, or log base e of 25 137ths, but also of e to the power of negative 0.046 t. So because these are inverses, we get cancellation there. We get the ln of 25 137ths on the left side, but we get left with negative 0.046 times our time over here. So to divide out this coefficient, no matter how ugly it is, we can divide it out. And what we're going to get is our time. And so the really neat thing about this is that we have a method for solving for time now, and also that we're getting to do a little bit more serious algebra. So taking a look at a decimal approximation for this, what would you suspect? Would it take longer or shorter to reach a temperature of 75 starting at 212 than it would for 70? So now in our last video we said to get down to 70 it took about, let me find this time here, it took about 33.8 minutes. But because the temperature doesn't have to drop as far in this, I would suspect that it's less than 33.8. Let's take a look at the actual value we get here on our calculator. So typing this in, we have the ln of 25 divided by 137. And we're going to take all of that divided by a negative 0.046. So dividing out, we get about 36.9, 37-ish minutes-ish. I'll put a 0.0 there, minutes. And we want to label units there. But yeah, a little bit less time because we didn't have to drop as far in temperature to reach room temperature. Cheers.